Great, thank you so
much. Please start.
Thank you. So, yep, this is my name. And I thought that today I could do this presentation on this board. So it would be a bit more interactive and understandable. So at the very beginning, I will give some overview of my talk, and then I'll go through it. So yeah, my talk is devoted to complete systems in bi-involution on classical Lie algebras, and I'm going to apply Kronecker's method to get this complete system of functions. And now I'll explain why. So at the very beginning, I will tell the motivation. The motivation comes from geometry. So I'll start with the complete system of functions in involution with respect to one Poisson bracket. Then I'll explain why we want to find complete system of functions in bi-involution. Then I'll tell that this problem is too hard and we will try to simplify it first. We will consider two brackets. One of them will be linear and another one will be constant. And this problem is still open and still too hard for us, and we will simplify it even further. Yes, when one of the brackets is linear, it means that our manifold, our Poisson manifold, is just dual space to Lie algebra, and we will simplify it like that. We will say that G is classical Lie algebra, and in that case, this problem is still open. And then I will explain how should work the algebraic approach. According to this algebraic approach, we consider these two brackets, two Poisson brackets, classical one and another one, as two skew-symmetric bilinear forms on some bigger vector space over some bigger field. And we will understand that in this algebraic language, a complete system of functions corresponds to some basis of some subspace. We will understand which one. And to find these bases, we will use Jordan-Kronecker canonical form. So if we have two skew-symmetric bilinear forms, there is a classical theorem from linear algebra that these two forms can be brought to some canonical form. This form is called Jordan-Kronecker. And yeah, as when we have Jordan normal form, we have a lot of Jordan blocks. Here there are blocks of two types, Kronecker type and Jordan type. So if we want to find this canonical form, we will have to find these two different parts. And for which part, for every part, I will explain how we can do it from just a very algebraic point of view. To find Kronecker part, we will use Kronecker method. Sorry, I will explain it. And for Jordan part, it will be even easier. And then, in case when this element A is regular, we will obtain some results and we will see what it means in this geometric, from geometric point of view. And when element A is singular, this problem was open, and I will tell my results. So which results I obtained, which and what was the construction. So the plan is like that. Let's start from the beginning. Like normally I don't go so deeper with this overview, but during the talk, it's too hard to follow that. So today I thought maybe it will help us if we see the whole view from the very beginning. Let's start here. So if we have Poisson manifolds, what it means? Yeah, I think that everyone here knows the definition. Yes, am I right? Okay, and yeah, maybe I have to say that one of the important example is symplectic manifold, and that if we have some Poisson manifolds, it can be represented as joint union of these symplectic leaves. And we have Liouville-Arnold theorem that says that if we found big enough system of functions in involution, then we can find good coordinates, action angle coordinates, and they have us. So here what we have, that if we have Poisson manifold, then we want to find this complete system of functions in involution. We have these functions. Involution means that if any two of them gives 0 when we take Poisson bracket, and completeness means that there are a lot of them. So this number of functions, and here rank of bracket, it's just a maximal dimension of symplectic leaf. Okay, so then here we can say that in many cases, okay, I will just show it here. Here we have some observation made of different scientists that in many cases, if we can integrate the system, then it's because of its bi-Hamiltonian nature. So it means that we had not only one Poisson bracket, but we had another one, and it was compatible with the first one. It means that if we take any linear combination of these two brackets, we will obtain another Poisson bracket. And so if we now have two Poisson brackets, we still can try to find complete system of functions now in bi-involution. And now completeness, it also means that the number of functions should be maximum possible. But in that case, maximum possible is just maximum of ranks of any linear combinations of these two functions. Okay, maybe you can see it here. Yep. And here maybe I'll try to give some examples and counterexamples. As we can see, the second problem is harder because here we have two brackets and more conditions. But we have a lot of examples when we can solve this problem, and it's really hard to find some counterexamples. So I have just a few slides with them. So normally, okay, I have to be sincere. So I'm not a very good expert in these next two slides. So normally I don't talk about it. So maybe you can correct me if you see something wrong. Yep. Examples when we have bi-Hamiltonian structures. There is a theorem of Filippo that in the neighborhood of an invariant toroid, any integrable Hamiltonian system is bi-Hamiltonian. But as I understand, the problem here is that if we had one bracket with respect to which the system was Hamiltonian, then then they construct two other brackets, and not just complete the system with another one bracket, but construct two new brackets. And they say that it has no direction direct relationship with the regional Poisson structure. And there are a lot of examples when this bi-Hamiltonian structure was found. So if you're interested, they can be found, for example, in this work of Bolsinov and Ashimkov. Yeah, so maybe we can talk about it later, but it's just one source of them. And counterexamples, what I found, it's just a theorem of Fernandez, and they say that yeah, there is some geometrical condition for system to be bi-Hamiltonian, but they are looking for bi-Hamiltonian system only in degenerate, non-degenerate sense. So for this theorem, one of the brackets must be non-degenerate. So for us, it's nothing. So for my case, it doesn't help, but it's like the only counterexample that I could find. So yeah, if we want to find some second bracket which is degenerate, then it's hard. But if we have no conditions about degeneracy, so like very stupid answer is that we always can add just 0 brackets because it doesn't change anything. Okay, so that was this part which is I don't know, hard and new for me about these examples and counterexamples. And yeah, so now we understood that we want to solve this problem with bi-Poisson manifolds, and that it's hard. And yeah, we try to simplify it like that. What it means? What does it mean? So if our Poisson manifold is dual to some Lie algebra, then linear bracket is just Lie-Poisson bracket. I will show it later how it looks like. And yeah, we will take another constant bracket as a bracket with frozen argument that could be constructed for any element of this dual space to Lie algebra. And yeah, in this case, symplectic leaves, they are just orbits of cojoint representation. And this number of functions could be found like that. It's 1/2 of dimension of Lie algebra plus index of Lie algebra. Okay, yeah, maybe I have to say here that, for example, if we are not trying to find a complete system of functions in bi-involution, but only in involution on some Lie algebra, then we have the result of Sadetov that, yeah, we can do it, but this result is not constructive. That's why it makes sense to go further, because yeah, this problem is not solved in constructive way. It's like the first reason, and the other one is that we still want to have some construction with respect to these both brackets. Okay, and like so our last simplification is that algebra Lie will be classical, and now I'll show how these brackets look like. So if we have classical Lie algebra, then we can identify Lie algebra and its dual space via invariant scalar product. And the first bracket, like Lie-Poisson bracket, is written like that. So if we have 2 functions, then to calculate this bracket, we take differentials of these functions. Then we take Lie bracket and take a scalar product of X and this element of Lie algebra. Yeah, and the second bracket is called frozen because this element R here is just a constant. Like in classical Lie-Poisson bracket, here we have our variable X, and here we just substituted it with some constant. Maybe now it's a good time to look at some examples. So how these two brackets work on some Lie algebra, and we will take, we will consider Lie algebra GLN because it's a bit easier for us. So it's just algebra of all matrices and by n, and here a scalar product is just a trace of product. So you can see it. And now let's try to, for example, we can take two functions, phi and psi, and we will try to calculate its brackets. So first of all, we have to calculate, maybe we can see both. We can see the definition here. We have to calculate differentials. How we can do it? So for example, for function phi, the differential of phi is just a trace of differential of x multiplied by 2x, and we want to obtain an element from Lie algebra. So we identify this linear function with the element of algebra 2x. And then we do the same thing for the second function, and then we can calculate two Poisson brackets. The first one is classical, so we can calculate this one. How I obtained this form is just because this scalar product is invariant in this Lie algebra. That it means that we can change the order of these variables, and we obtain 0. And for another Poisson bracket, we also obtain. We also obtain 0. It means that these two functions, phi psi, are in bi-involution. Okay, do you have some questions?
I think it's okay for the moment.
Great, thanks. I think it's time to say that I said that this problem is still open, but if element A is irregular, then we have some very classical argument shift method by Mishchenko and Fomenko. This method could be obtained through this algebraic approach. And now we will see how to do it. So our algebraic approach is to consider these two brackets as skew-symmetric bilinear forms on some bigger vector space and field and over some field. So let's guess what should be the field and what should be the vector space. So here, for example, for classical bracket, we have to multiply by element x. It means that we want x be in our vector field. So our vector field will just a field, it will be field of all rational functions on Lie algebra. And we have to understand what is the vector space. So here we know that differentials of functions have to be in this vector field. So we will obtain the product of the algebra and this big field of rational functions on G. In terms of Lie algebra G, this field is just a field with n square variables. So it's just rational functions of these n square variables, and elements of this field, it's just a matrix n by n with elements from this field. And yeah, now we can see that these brackets correspond to these skew-symmetric forms on some, on this vector field, vector space, and over this field. Okay, let's understand what it means for our complete system functions in bi-involution. So as we remember, completeness of this system means that M is maximum possible, and bi-involution means this thing. What it means? What does it mean in terms of?
Sasha, I'm sorry, I don't understood the role of the space V. Is it for constructing the graduate Lie bracket, such that the linear one is calculated on element of G and give an element of G, and the scalar one calculated from the element of G gives the constant.
Sorry, what does it mean, role of V?
The role of the space V in the construction. Normally, the bivector is the bivector on a manifold, so it.
Yeah, and here B is just skew-symmetric bilinear form. Bilinear forms are defined on some vector spaces.
Okay.
Yeah, so it's like very algebra. So now we have this problem. It's just a problem from linear algebra. We have two skew-symmetric bilinear forms. So no b-vector, nothing like that. Like very pure linear algebra, but with very big vector space.
Okay, thank you.
Great, thanks. And now we want to understand what these two conditions mean in terms of this linear algebra thing. So we know that we want to, so this means this, that if two functions are in bi-involution, it means that their differentials give 0 when we put them in both skew-symmetric bilinear forms. And the number of these functions should be maximum. So in terms of linear algebra, it means that these differentials, they form a basis of bi-Lagrangian subspace. Yeah? Because it's just the definition of bi-Lagrangian subspace, so it should be isotropic with respect to both skew-symmetric forms, and it should have maximum possible dimension. So our problem is, our goal is to take these two skew-symmetric bilinear forms and somehow find a basis of bi-Lagrangian subspace. And then when we obtain these differentials, we want somehow to integrate them, and we will complete and we will obtain a complete system of functions in bi-involution. Now the question is, okay, we have these two skew-symmetric bilinear forms. How we could find this basis of bi-Lagrangian subspace? And from linear algebra, we know that we can take these pair forms, bring it to Jordan-Kronecker normal form, and then like halves of these spaces in which our matrices have this Jordan-Kronecker form, they will form a basis of bi-Lagrangian subspace. Maybe it sounded too complicated, so yeah, I will show first of all blocks that are in this theorem. So this we have some Jordan-Kronecker theorem, very yeah okay, some result of just pure linear algebra, and it says that if we have two skew-symmetric bilinear forms, then we can find a basis so that these two forms simultaneously will be presented in such a way where we have two different types of blocks, Jordan blocks and Kronecker blocks. And yeah, that's all. And what I tried to say that if we found a basis in which our two skew-symmetric bilinear forms have this form, then we can take half of this basis. So if we take these elements of basis that correspond to the second half of Kronecker blocks and that correspond to the second half of Jordan block, then they will form a bi-Lagrangian subspace. So obviously they will form bi-isotropic subspace because these vectors, when we calculate bilinear form on these vectors, they give 0. So it means that yeah, these second halves of every block they form a bi-isotropic subspace, but if we calculate their number, we understand that it's like a maximum possible number of elements. So yeah, to obtain this basis, it's enough to find this basis for canonical form. I will call this basis like I will call it canonical basis.
Sasha,
It's not unique.
that you try to apply the Jordan-Kronecker theorem for the infinite dimensional situation.
When
Space V is infinite dimension.
No. The space is n squared dimensional.
The space V.
Yeah. Field is big, but
B is a skew-symmetric form on the space V, and V is an infinite dimensional space.
For example, when sorry, I have to
no, it is written here that is G multiplied by the rational function on G.
Yeah.
So it is infinite dimension.
No. No. Okay, if we have, sorry.
Yeah, okay, but the question is over which field? You mean the over
this big? Yeah. The thing is that, yeah, that's what I tried to say, that our skew-symmetric forms, we consider them as forms on this vector space over this field. And when we look at this vector space over this field, the dimension of it's just dimension of Lie algebra.
I suppose that V over K is just G.
Okay, so for example, if G is G ln, then V it's just
Okay.
Okay. So
no, what means just G? The field K becomes not algebraically closed. So that's. But I have another question. It is important that the ground field is C. We can take any algebraically closed field here of characteristic 0.
As far as I understand, yeah, so I've never seen when everyone takes another field except C. So, but I'm pretty sure that if we take another, yeah, closed, yeah, yeah, so it will work.
Okay.
But
sorry, but you say that the Jordan-Kronecker form is a correct method over such a field?
Here I will also say it. In general case, lambda here could be any element of field K, but when we have our these skew-symmetric forms B and BA, maybe, okay, I will show it right now. We know that Jordan part consists of blocks with eigenvalue infinity. It means that, yeah, for us, it's not important here which, yeah, some properties of the field C, because for us, the only important eigenvalue is infinity.
Maybe it's true, but it's a little bit strange for me that the Jordan-Kronecker canonical form exists over such a field, which is a field of rational functions. Is it right or not? Or it demands some ramification?
We have yeah, we need to have such a theorem. We need algebraically closed field. But if in our case we need we know that the eigenvalues will be only infinity, then it's not important to that. Yeah, if we know that Jordan part will be very simple. I can even show it here somewhere. So we know that our Jordan part will look like that. Then the first form will look like that, and the second one like that. So in that case, yeah, for us it's not important to have algebraically closed field. Like, yeah, we a priori know that Jordan part will be simple. That's why this Jordan-Kronecker theorem still works for this case.
Okay, I need some time to understand this, this subtlety. Please continue.
Great, thanks. Yeah. Okay, I don't have too much time. So here I had written some algebraic motivation, but maybe I'll just throw it. So I wanted to explain why this problem to find canonical form of these two skew-symmetric bilinear forms is interesting. And the answer is that if we have some Lie algebra, we can consider another skew-symmetric bilinear forms like that are defined on this Lie algebra. By this equality, and these bilinear forms, they correspond to adjoint operators. When we identify G and G star, then this form corresponds to adjoint operator, and there is some heuristic, like when we study adjoint operators and its invariants, it's a very good approach to have some yeah, to obtain some properties of Lie algebra. For example, when we study these operators, we can have classification of semi-simple Lie algebras, and so that's very natural also to study the invariance of these bilinear skew-symmetric forms. But if we try to find invariance only of one skew-symmetric bilinear forms, it's nothing interesting. It's just its rank. So let's take two skew-symmetric bilinear forms of that form and try to find the invariance. And the idea is that one element is fixed and another comes from open-end subset of Lie algebra, then Jordan-Kronecker invariance of this pair are equal to Jordan-Kronecker invariance of our pair of forms. I'm sorry, and there you shouldn't have C, have just our two symmetric bilinear forms. So yeah, I would go further, and if we have time, I could tell more about that. Okay, so now about this canonical form, there are some invariants, and we already know that for Jordan part, we have no invariance because we already know everything about these blocks. And for Kronecker part, there are some invariants. They called Kronecker indices, and they are just dimensions, half of dimensions of these blocks. So if yeah, Kronecker block, it's always of odd dimension, and the half of it is called Kronecker index. So our idea would be, also one of goals would be to find these indices. And how we can do it? We can apply Kronecker method. It works for any pair of skew-symmetric bilinear forms, but we will apply it for our forms. There are 3 steps. The first one, we have to consider submodel of some big model over some big field, like that. Then we will find a minimal basis of this submodel. And here, minimal means that leading coefficients of this basis must be linearly independent. And if we found this basis, then degrees of this basis are Kronecker indices, and coefficients of this basis, they form these second parts of canonical basis for Kronecker blocks. Okay, we will consider some example a bit later. Yeah, maybe, okay, let's do it a bit later. Now, and yeah, now we will go to regular elements. If element A is regular, then we know that there is nothing in Jordan part, and we need to find just the Kronecker part. How we can do it?
Sasha, excuse me. Could you give, if you know, just one simple observation why the Jordan part is trivial?
For example, we can just calculate the number of, so for example, if we want to calculate the rank of one of the forms, I have to, okay, let's go here.
If it is not one line, we can discuss it
No,
later.
it's just, it's, If we calculate rank of matrix BA, okay, maybe it's not the explanation. It's just when A is regular, yeah, we just calculate these numbers, and
Okay.
it will say us that here we have nothing.
Okay, we can discuss it later. Please continue.
Okay, if we look at rank of matrix BA, Jordan part doesn't give us any anything to rank, and here we will obtain just doubled sum of Kronecker indices, and in Jordan case, this doubled sum will be already the number of elements in this incomplete system of functions in bi-involution. So yeah, so already this part will be big enough.
Thank you.
And yes, we have this lemma. So first of all, we have to consider some submodel like that. And in our case, we know that it's generated by differentials of basis invariants, like that. And yeah, maybe now it's time to look at example of Lie algebra G. So if we talk about GLN, then basis invariants could be just trace of powers. In that case, the differentials would be just powers of matrices, and this modular submodule will be generated by these elements. So it's just yeah. And the second step of Kronecker method is to find minimal basis of such a submodel. So we have this submodel, we already have some basis, and we have to check if it's minimal or not. Minimal means that leading coefficients are linearly independent. Which linear coefficients we have here? It's just here it's just identity matrix, then it's matrix A, then it's matrix A squared, and we go till A to the power n minus 1. And so it means that if element A is regular, that if its powers are linearly independent, then this basis is already minimal. Yeah, so if element A is regular, it could be reformulated that every eigenvalue correspond for every eigenvalue we have only one Jordan block. So here we could see that for regular elements, Kronecker method, we don't need we shouldn't make this second step because the initial basis is already good. So for any reductive Lie algebra, it works like that. We can take this initial basis. It's for regular element A, its leading coefficients would be linearly independent. And it means that Kronecker indices, it's just degrees of basic invariance -1, and that this basis is just the coefficients of these differentials of basis invariants. Yay, cool. So these coefficients, they form a basis of B-Lagrangian subspace. So we solved this problem from linear algebra, and now we have to make the last step to integrate these functions. Yeah, here we have coefficients of differentials, and now we have to integrate coefficients of differentials. So it means that we obtain just coefficients of initial functions, and it means that we obtained shift argument method. So applying this Kronecker method to a pair of forms B and BA, we obtained shift argument method in case of regular element A. Yeah, do you have some questions here and now?
Me not.
Great. So yeah, my goal was to apply the same thing in the case of singular element A. And here I just show the results. So for Lie algebras GLN, SLN, and SP2N, the problem was solved for any element A. For the case of SO2N plus 1, I could find a Kronecker part in two cases, in case when element A is good and when element A is correctable. And for good elements A, I could find even a Jordan part. And the most difficult case was type D. Here I also could find the Kronecker part for good and correctable elements, and completed to Jordan to the whole.
Can I ask what good and correctable mean, please?
Yeah, sure. I will show it just a few seconds. Yeah, so first of all, I will show how we can construct a Young diagram if we have some element A. We just, for every eigenvalue, we construct a Young diagram. Yeah, I think it's understandable here. And then we just take all the diagrams and just take the sum of them. So for example, in the second line, we had two squares. So here we also have two squares. So yeah, for every line, we just summed all the squares. That's how we construct Young diagram by elements A. And good elements are such elements that our first row is odd number, and next rows they have the same remainder. So every two of them have the same remainder when we divide by 2. So 2 odd or 2 even, for example, and so on. The last one could be just any. So for example, this one is not good because, okay, this is odd, that's good. These are over this, they have the same remainder, but these have different, so this element is not good. And what is correctable? Correctable elements is always nilpotent element. And here we just take a diagram of good element and add some even rectangular. So this is 2 and this is 6. If both dimensions are even and we added this part to some good diagram, then this diagram is called correctable. And also there is a second type of correctable elements. It's just type with 4 rows, where first 2 rows are of the same length, and the second 2, so third and fourth, are also of the same length. These are called correctable. I have a normal definition in the presentation, so you can read it there. Okay, and I'll try to do it really fast. Here, maybe I won't talk about it. Here I have some like geometrical explanation why types A and C are simpler than types B and D. If we look at sheets of Lie algebras, then for these types, when we take element A from the sheet, then Kronecker indices are always the same. But for other 2 types B and D, we constructed counterexamples. So it's just like an explanation how we can see that these cases a bit harder than this one. And also...
Sorry, what is a sheet of Lie algebra?
What is what? A sheet of Lie algebra. If we take all the orbits of some dimension and we take union of them, and then we take irreducible components, then these irreducible components called sheets. For the case of GLN, for example, sheets are the elements that correspond to the same Jung diagram.
Thank you. Thank you.
Maybe I can show it here if we prefer. Yeah, here we can find maximal irreducible sets consisting of G orbits of fixed dimension. Yeah, I've told it wrong, but yeah. Sorry. Okay, I have 7 more minutes, I think. Okay, I tell about this part, limits. It's just how these results could be integrated to the big theory. If we consider some Mishchenko-Fomenko subalgebras, then we can also look at limits of Mishchenko-Fomenko subalgebras. And this complete system of functions in bi-involution that I constructed here, they freely generate some of these limits. So we could say that, okay, we found nothing more because nothing new, because they generate already known subalgebras. But on the other hand, for these subalgebras, now we know it's freely free generators. And finally, I'll try to give the construction of both sides of these spaces and of complete system of functions in bi-involution. So let's start with, I'll try to do it like in historically. First of all, I found this minimal basis in case when element A is nilpotent. It was not too hard. I knew that if we take characteristic polynomial of matrix X minus TA, and if I put X minus TA as a variable here, I will obtain 0. So my idea was to, if I want to have minimal basis, like something very small, then I could use something very similar to this characteristic polynomial. And I used these, I don't know, smaller or characteristic polynomials for the matrices of smaller sizes. So I just took several, like few coefficients And then if I put my element x minus ta as a variable here, I will not obtain 0, obviously, but I will obtain elements that are minimal basis of module z. So it was like the first result. It works only for nilpotent elements. Then idea was how could we generalize this result, and there was this observation that these I don't know, shortened characteristic polynomials, we can obtain them by induction when we divide the characteristic polynomials with a remainder by z. So I obtained this inductive method, how we could obtain some similar polynomials. So we start with the characteristic polynomial of matrix x minus ta divided by some by this z plus eigenvalue multiplied by t. Then we have some new quotient. We call it by q, for example. Then we divide it once again, have new quotient, and go so on. And yeah, thus we obtain n quotients. And the theorem is that if we take these quotients and substitute x minus ta as this variable z, we will obtain minimal basis of z. And then when I had to calculate, integrate this basis, I just found explicit form of these matrices, and I could integrate them. It was not very beautiful, but then Ernest Borisovich Winberg, my scientific advisor, he noticed that, it was like very unexpected, that when we try to integrate these quotients, we will obtain reminders that we have during this division. So it's like, I don't know how he could find it, but that's why we have the theorem for all coefficients that if during this division process we will consider all these reminders, then these reminders they are polynomials they depend on t. And if we take all the coefficients over t, then we will obtain Kronecker part of complete system of functions in bi-involution. And it means for the nilpotent case, when we integrate these elements, we will obtain just coefficients of characteristic polynomial. And I'd like to say how it works in the nilpotent case, but I think my time is over. So do I have 2 or 3 more minutes or not?
Yes.
Great.
Please.
Thank you. So let me just show how it works when element A is nilpotent. So the what was the conclusion here? That obviously it would be much easier just to find these elements and don't use this big journey with all this algebraic thing and integration. Maybe it would be easier just to find these functions and to prove that the coefficients complete Kronecker part of functions in bi-involution. So that's why when we started to search or to calculate Jordan part, we already worked in the geometrical parts of this table. So, okay, if we have nilpotent element A, what I've tried to explain is that how we could find a complete system of functions in bi-involution. First of all, we want to obtain Kronecker part. So we take characteristic polynomial, then we take its coefficients, then we substitute x. So it means that we take coefficients of this polynomial and we obtain, and when we take its coefficients over variable t, we will obtain some elements, some functions, and these functions, they form a Kronecker part. If element A is regular, then all these columns, they will be of size. So for example, this has one element, this two. The last one will consist of n elements. But if element A is singular, then these columns could be shorter. So this Kronecker part doesn't give us the complete system of functions in bi-involution. But what we noticed that these elements with a frame, they form a basis. They are basis invariants of a kernel of a form BA. And okay, I didn't show it and I didn't tell it, but how we can find a Jordan part, we just take some elements. So if we want to find these elements, these second halves, we could do it like that. We want to find, we want to be in the kernel of form BA, so the second one. So yeah, like here. And we want to find vectors that form a just Lagrangian subspace with respect to this form B. The thing is that kernel of BA consists not only of these vectors, but also of these vectors. So to find the Jordan part, we have to take all these vectors because they also belongs to a kernel of BA, and then extend these vectors to the Lagrangian subspace of kernel with respect to the form B. And here we just understood that these elements, they are basis invariants of this kernel. And it means that if we want to find some bases that correspond to Lagrangian subspace with respect to form B, in geometrical language, it means that we want to find complete system of functions in bi-involution on this thing. How could we do it? So yeah, obviously we could just use argument shift method, because we already know basis invariants, and we just take this basis invariants, we shift argument once again, and when we shifted the argument, we obtained the other elements that will give us a Jordan part. So for this nilpotent case, we can, I don't know, call it like double shift method, because initially we shifted this argument here to our singular element A, took the coefficients, and when we get not enough coefficients, we just shifted the argument once again by another regular element B, and got some other coefficients that will give us a Jordan part. So yeah, that's, I think it's in this nilpotent case, it looks pretty elegant. So yeah, here I'd like to finish my talk. And yeah, in case of any element A, the thing is very, very similar. Just it will be not characteristic polynomial and these coefficients, it will be these quotients. Oh, sorry, not quotients, but reminders. Yeah. Thank you so much. Do you have some questions?
Yes, thank you. Very interesting. But is it efficient, this method of double shift in all cases? Why you don't use it in all cases of the element A?
Or for regular?
No, not for regular.
For nilpotent? No, it works, this like double shift, it works for all the cases, but the beginning will be different. It's not the coefficients of characteristic polynomial, it will be these reminders. But if we if we have our reminders here, we take its coefficients, and then the last of them will also be a basis invariance of kernel, and we also could shift argument here and obtain this part. So yeah, this like the second part with like second shift works not only for nilpotent but for everything. Okay, and not for everything, but for these cases. So yeah, here we could do it for any element, and for the algebras B and D, we wanted to element A to be semi-simple, so that we knew that these.
Okay, not enough.
Mhm.
So, but am I right that this table is if and only if? So the method you explained could not work for other element, for example, for SO2N.
No, I wouldn't say so. It's just I couldn't do it. So for example, here I just found some elements that give us something, and then I could integrate, but yeah, maybe it was just me who couldn't find it.
Thank you very much. It is very interesting. Are there any questions? Other questions, please? Okay, if not, I'd like to thank you once again, and we stop now.